Chapter 8, the quantum mechanical model of the atom. This is one of my favorite quotes that's in this book. It's a quote from Niels Bohr, who is one of the guys involved in the development of quantum mechanics. Anyone who is not shocked by quantum mechanics has not understood it. So that might give you a clue as to the kinds of stuff we're going to see in this chapter. So until the early 1900s, it was believed that all physical things that happened were deterministic, meaning that if you know the current state of something, you can predict what it's going to do in the future. So if you shoot an arrow, not an electron, if you shoot an arrow or throw a baseball in a certain way, and you throw another baseball or shoot another arrow in exactly the same way, where do you expect the second one to land? Really close to where the first one landed, right? Because if you do the same thing to the same object, the same thing should happen. But in quantum mechanics, that's not true. If you shoot an electron down a path and measure where it lands, and you shoot a second one down the path under the same conditions, it will almost certainly land somewhere else. This is disturbing. This does not make sense in terms of what we know in the physical world that we can see. So this was a lot of famous physicists that discovered this. For subatomic particles, the present condition does not determine the future condition. So we're talking here about the quantum world, or the absolutely small world. This is the world that the electron belongs in. And these objects behave differently than those in the larger macroscopic world. So, crazy thing, absolutely small particles like electrons, when unobserved, can be in two or more states at the same time. So an unobserved radioactive nucleus can be simultaneously emitting a particle and not emitting a particle. An electron can be a wave and a particle at the same time. It's hard to get your mind around. So we are talking about very, very small things here. So to give you the idea of the size of an electron, if you think of a single speck of dust, a little teeny tiny thing you can barely see, right? The speck of dust has more electrons in it than the number of all the people that have ever lived on Earth. Not just the current living people, everybody in total. That's a lot of electrons in a speck of dust. Electrons are important because they determine a lot of the behavior of atoms. And directly observing electrons is impossible, and even indirectly observing them causes their behavior to change. These guys are just really squirrely. So, Schrödinger's cat is a famous thought experiment that just demonstrates how quantum strangeness does not transfer to the regular macroscopic world. So I've got two different videos that we're going to watch here.
To build the Honda CR-V.
This wouldn't be a YouTube channel without a cat video. So without further ado, we present Schrödinger's cat. I'm sure you've heard some version of this famous thought experiment. You put a cat in a bunker with some unstable gunpowder that has a 50% chance of blowing up in the next minute, and a 50% chance of doing nothing. The gunpowder is Einstein's version. Schrödinger preferred poisonous gas. But whatever. So until we look in the bunker, we don't know whether the cat is dead or alive. And when we do look, it is either dead or alive. So if we repeat the experiment enough times with enough cats and bunkers and gunpowder, we'll see that half the time, Kitty survives, and half the time, Kitty goes bye-bye. The quantum mechanical interpretation is that before we look, the cat is in a superposition. It's both dead and alive. And our act of looking forces nature's decision. So our curiosity kills the cat. But what about the cat's perspective? Well, the cat either sees the gunpowder explode or not. So inside the bunker, we actually have these two possibilities. The powder explodes and the cat sees it explode, or the powder doesn't explode and the cat doesn't see it explode. There's no option, the powder explodes and the cat doesn't see it explode. So the cat's reality becomes entangled with the outcome of the experiment, and It's our observation of the experiment that forces nature to collapse to one option or the other. But we're like the cat too. Either the cat dies and we see it dead, or the cat lives and we see it alive. So who's observing us to force nature to collapse to one reality? Or do both possibilities happen in parallel within a larger multiverse? This collapsing to one reality problem is one of the biggest unanswered questions in quantum physics. So for Kitty's sake, can I has answer, please?
So this is from a great channel called Minute Physics. And then, this one.
To make a laser, all you need to do is give a big collection of atoms enough energy so they're excited and ready to emit
I
light.
don't think that
Okay,
Once one of
I
them
was afraid of that.
spontaneously emits a photon, it'll stimulate some of the others to do so, and you get a nice cascade.
Okay. I knew I should have closed that.
Hello and welcome to I Don't Think That Means What You Think It Means, where we look at bits of scientific theory that have wiggled their way into popular culture and have taken on a life of their own. Today we're talking about Schrödinger's cat, a famous thought experiment devised by the Austrian physicist Erwin Schrödinger, who helped piece physics back together after Einstein and his crew blew a giant frickin' hole in it back in the early 20th century. It's hard to overstate how much of a giant crap circus the 1920s were for physicists. Until then, everything had pretty much just been good old-fashioned Newtonian physics where you could observe objects moving and predict how they react to various forces. But then along comes all this new research into subatomic particles that shows that they don't act predictably at all. In fact, sometimes stuff seems to be two different things at once, like an electron and a beam might act like a particle sometimes and like a wave at other times. And to make things even more the more you try to observe and measure these particles, the less naturally they behave. Think to say, what now? My friends, I shall now introduce you to one of the biggest mind flogs of quantum mechanics. It's called superposition. The idea that a particle can exist in all of its theoretically possible states at the same time. So Schrödinger came up with this thought experiment to help everybody understand it. Say you have a cat, and you put the cat into a steel chamber for an hour with a vial of deadly gas, a Geiger counter, a hammer, and a tiny bit of something radioactive. Bear with me here. I'll say that there's a 50-50 chance that one of the radioactives is going to decay and release some radiation within that hour. If one of the atoms decays, the Geiger counter is going to trigger the hammer, shattering the vial of poisonous gas. Really, Schrödinger? This is not the best way to get people behind the idea of funding the sciences. So there's a 50% chance that at the end of the hour, that vial has been broken and the cat is dead, and an equally good chance that the vial hasn't been broken and the cat's just kicking it with what's for supper. But what's actually happening in the box? According to quantum mechanics, any one of those radioactive atoms would be in a superposition of being both decayed and not decayed at the same time. Because that's how quantum objects act. So then, that decayed atom will have both killed and not killed the cat, right? Well, that's the logical conclusion, but a cat isn't a quantum object. A cat is a big, normal thing that obeys nice, old-fashioned Newtonian laws, so it, just like every other cat in history, is either alive or dead. Schrödinger's point, at least one of them, is that the two objects are subject to two separate sets of laws that can't be reconciled. In order to know whether the atom has decayed or not, and whether the cat is dead or not, you have to open the box and see. But in quantum mechanics, the state of superposition can't be observed. So when the evil mad scientist finally opens the chamber to observe, the superposition collapses and the outcome is ensured. Today, Schrödinger's cat is often talked about as some kind of undead zombie cat, or discussed as if the cat is actually both alive and dead in the box. But Schrödinger's point wasn't to prove that you can make a cat be both alive and dead, but instead to prove that the quantum world doesn't mesh together well with the, like normal world. And alternatively, the point is that the universe is pretty frickin' weird. There are other interpretations of quantum mechanics that might resolve the paradox, but none of them are particularly easy to test. My favorite, of course, is the many worlds interpretation that states that at the end of the experiment, and at the end of every superposition, new alternate universes are created. In this case, one in which the cat is alive and one in which the cat's dead. And to be clear, I don't like this interpretation because I think it's the most likely one. I like it because I think it's such an excellent plot device for science fiction novels. If you have any questions, and I'm sure you do, ask them in the comments below and I'll, do my best. Also, if you have an idea for I don't think that means what you think it means, please let us know about that too.
New
ocean has been the centerpiece of my book.
So, anybody have any questions? Kind of weird, right? So these are some quotes from famous scientists working on this stuff. Again, Bohr saying, anyone who is not shocked by quantum mechanics has not understood it. Schrödinger, of Schrödinger's cat, wrote, I don't like it, and I'm sorry I ever had anything to do with it. Albert Einstein attempted unsuccessfully to disprove quantum mechanics until he died. He didn't like it either. Nobody who was working on this liked it. And I don't know that there's anyone who truly understands it. So, are we going to understand quantum mechanics in this chapter?
Just skip it.
It's tempting. It's tempting, believe me. We can get a lot of benefit out of the quantum mechanical model without actually understanding most of it. And so we're just going to try to get what we need out of it to do the problems in the homework and on the exams. Okay. So why do we even care about this theory, this model? It explains the manner in which electrons exist and how they behave in atoms. It helps us to understand and predict the properties of atoms that are related to the properties of electrons. Some of these things are, why are some elements metals and others are nonmetals? Why do some elements gain 1 electron when they form an anion and others gain 2? Why are some elements very reactive and others are practically inert? There's a whole bunch of periodic trends, patterns in the properties of elements in the periodic table. And quantum mechanical model explains those trends as well. The good news is we can use it to predict a lot of good stuff without actually having to understand it very deeply.